In question number 1, we have to solve the equation e power x plus 2 e power minus x upon e power x minus 3 equals to 4. So in the first step, we can just simply cross multiply. We'll get e power x plus 2 e to the power x is equals to 4 e power x minus 12. Now we can write this as e power x plus 2 upon e to the power x is equals to 4 e power x minus 12. Now we can take a substitution. So let's say we write y is equals to e power x. We can write the equation as y upon 2 upon y equals to 4y minus 12. Taking the LCM, we'll get y square plus 2 upon y equals to 4y minus 12. Now cross multiplying, we'll get y squared plus 2 is equals to 4y squared minus 12y. Then bringing y squared on the right hand side. So 4y squared minus 5 squared, that will be 3y squared minus 12y, and plus 2 will become minus 2 equals to 0. Now solving this quadratic equation using the quadratic formula. So we'll get y is equals to its minus b. So this will become plus 12 plus minus b squared. So 12 squared minus 4 into 3 into minus 2. 4ac upon 2 into 3. Now it's very important that we show the working over here for the quadratic equation, as there's a mark uh, in the exam for showing the working for finding the roots of this equation. So now once we have shown this, now we can substitute this into the calculator. So we'll get 144 plus 24. So 12, and then we'll square root the value. We'll get 12.96. So we'll get 12 plus minus 12.96 divided by 6. Now, with y is equals to e power x, y has to be a positive value. A negative value is not possible. So what we'll have is y is equals to 12 plus 12.96 divided by 6. So we'll get 12 plus 12.96 divided by 6. That is equals to 4.16. So y would be is equals to 4.16. And finally, we know that e power x is equals to y. So we can write e power x equals to 4.16. Introducing ln on both the sides, we'll get x ln e is equals to ln of 4.16. Substituting this in the calculator, we'll get 1.4255. So x would be is equals to 1.4255. And as we have to give our answer to 3 decimal place, so the final answer will be 1.42426. Question number 2a, we have to expand the expression 6 minus x, 1 minus 2x power minus 3 upon 2 up to including the term in x squared. So 6 minus x will remain as it is. To expand 1 minus 2x to the power of minus 3 upon 2, we'll be using the formula 1 plus nc1 b to the power 1 plus nc2 b to the power 2. And we won't have to go further than this, as we have to only expand up till x squared. And what we should know is that nc1 is n and nc2 is n into n minus 1 divided by 2 factorial. So writing 1 plus nc1, and n is minus 3 upon 2. So nc1 is n, will get minus 3 upon 2 times by b. So b is minus 2x plus nc2. So that will be minus 3 upon 2 into minus 3 upon 2 minus 1 divided by 2 and times by minus 2x whole squared. So this will become 1, and this will be minus minus will be plus. So plus 2 and 2 cancel. So this will become 1 plus 3x, and minus 3 upon 2 minus 2 is minus 5 upon 2. So minus 3 upon 2 into minus 5 by 2, that is 15 upon 2. And the 2 goes in the denominator. So this will become plus 15 upon 4 into 4x squared. 4 cancel. So the expansion is 1 plus 3x plus 15x squared. Now multiplying it with 1 minus 6 minus x. So we'll get 6 minus x multiplied by 1 plus 3x plus 15x squared. So 6 times 1 will be 6 plus 18x plus 6 times 15 is 45x squared minus x minus 3x squared and then minus x times 15x squared will be 15x cubed. So that term is not needed. Now simplifying this, we'll get 6, 18 minus x is 17. So we'll get x6 plus 17x. 45 minus 3 will be plus 42x squared. And that will be the final expansion. Now it says state the set of values of x for which the expansion is valid. Now what we need to remember is that in this expansion 1 minus 2x to the power minus 3 upon 2. So this is what we learned initially with theory, that b, this term b over here, must the modulus of this term, so this must be less than 1. So we'll get x will be less than 1 upon 2. So that we can leave our answer like this. And as modulus also means positive and negative, we can also give our answer as greater than negative 1 upon 2 and less than 1 upon 2. Both answers will be marked correct. In question number 3, we have to make an Argand diagram and shade the region whose points represent complex number z which satisfy these two inequalities. Now, the first thing that we should always do with these Argand diagrams is that when it is given in this form, we write it as z minus, and this will be written as 0 plus 3 iota less than or equals to 2. And this will be written as 1 upon 4 greater than equals to argument of, we'll write it as z minus and write it in the bracket. So this will be 1 plus 2 iota less than equals to 3 upon 4 pi. Now, what this means is that the distance of z from this point is less than or equals to 2, and the argument of z from this point is between 1 upon 4 pi and 3 upon 4 pi. So now we can make the x and the y axis. Now this point 0 comma 3 iota, we know that y axis represents the imaginary axis. So 0 plus 3 iota basically means 0 comma 3. So we'll come at 0 comma 3. Let's assume it is over here. And we have to make a circle of radius 2. So if this is 3, let's assume that this is 5 over here and this is 1. So we'll make a circle of radius 2. And let's assume this is 5 over here. Now, once we have done this, now it says now this actually also means that z is anywhere on the circumference or within the circle. Less than equals to 2 means from this point, z is anywhere within the circle. Now, in the next part, it says that the argument of z from 1 plus 2 iota. Now, if this was z, this was 2, and let's say this is 1, and this would be 2 over here. So the argument of z from 1 plus 2 iota, so let's say this is 2 over here, is between 1 upon 4 pi. So if I make imaginary line over here, 1 upon 4 pi is roughly 45, so we can make it like this. And 3 upon 4 pi is 135, so it would be in this direction. And as the angle is in between and the area is within the circle, so we will be shading this area over here as the argument within this area is between 1 upon 4 pi and 3 upon 4 pi, and also the modulus or the distance is less than or equals to 2, which basically means it is within the circle. And this is the area that we'll have to shade. In question number 4, we have to solve the equation 3 cot x minus 4 cot 2x equals to 3. We know that cot is 1 upon tan, so we can write it as 3 upon tan x minus 4 upon tan of 2x equals to 3. Now for tan of 2x, we can use the identity that's given in the formula sheet. So we can write it as 4 upon, and for tan 2x, it is 2 tan a upon 1, 2 tan x upon 1 minus tan square. So we can write it as so this will be 2 tan x divided by 1 minus tan square x. So this formula is given in the formula sheet equals to 3. So 1 minus tan square x will come up in the numerator, and we can write it as 3 upon tan minus 4 into 1 minus tan square divided by 2 tan equals to 3. Taking the LCM first, so the LCM will be 2 tan. We will get over here, so this will become multiply by 2. This will multiply by 2. We'll get 6 minus 4 plus 4 tan squared is equals to 3. Multiplying 2 tan on the left hand side, we'll get 2 plus 4 tan squared, and that will be is equals to 6 tan. Now, bringing the 6 tan on the left hand side, we'll get 4 tan square minus 6 tan plus 2 equals to 0. We can divide the equation by 2 to simplify and write it as 2 tan square minus 3 tan plus 1 equals to 0. Now, solving this equation quadratically, we can apply middle term breaking maybe in this case. So let's see if we can do it. 2 tan square minus 2 tan minus tan plus 1 will be equal to 0. So yes, we can use middle term breaking. We'll get 2 tan common. So tan minus 1 minus taking 1 common, we'll get tan minus 1 equals to 0. So once we have solved this, we'll get 2 tan minus 1 into tan minus 1 equals to 0. So tan x would be equals to 1 and tan x would be equals to 1 upon 2. Now, what we have to be careful about is this range over here, or the domain of x. So that is always between 0 to 180. So tan is positive in the first quadrant and the third quadrant. But as we only have the domain from 0 to 180, so all of these ratios are positive in the first quadrant. So taking tan inverse of 1, that is equals to 45. So we'll just make 45 in the first quadrant, and that would be it, as the other answer would be more than 180 if we measure it anti-clockwise from the x-axis. And the second answer would be taking tan inverse of 0.5, and that answer would be 26.56. So x would be equals to tan inverse of 1 upon 2. And when we substitute that in the calculator, then that is 26.56. And to one decimal place, we'll give our answer as 26.6 degrees. And that will be the only two answers that we'll have for this question. In question number 5, the square roots of -1 minus 4 root 5 iota can be expressed in the form x plus iota y. By first forming a quartic equation in x or y, we have to find the square roots of -1 minus 4 root 5 iota. Now, this is a complex number, 1 minus 4 root 5 iota, and the square root of this number will also be a complex number, which is x plus iota y. Now, to find the square roots, we'll whole square both the sides. So we'll get, if we expand the right hand side, so this will remain as it is without the square root sign, and this will become x square plus 2xy iota, and then plus iota square y square, which will be equals to minus y square, as iota square equals to -1. So now comparing both the sides, the constant term on the left hand side is -1. On the right hand side, that is x square minus y square. And then the coefficient of iota is 2xy. And on the right hand side, that is minus 4 root 5. Now we'll use these equations to form a quartic equation, the quartic equation, and then find the values of x and y. So let's say x is equals to minus 4 root 5 upon 2y. This will cancel out. So x would be equals to minus 2 root 5 upon y. Now in place of x, we'll substitute this value. So 1 minus 1 would be equals to minus 2 root 5 upon y whole squared minus y squared. Expand whole squaring, we get -1 is equals to, so 4 into 5, that will be 20 upon y squared minus y to the power 2 again. Taking the LCM, so this is multiplying by y square. You will get 20 minus y to the power of 4 divided by y squared equals to -1. Cross multiplying, we'll get minus y squared is equals to 20 minus y to the power of 4. making y to the power of 4 positive, we'll get y power 4 minus y squared minus 20 equals to 0. Now, this is a simple quadratic equation. We can solve it like a quadratic equation by midterm breaking. We can write it as y power 4 minus 5y square plus 4y square minus 20 equals to 0. Taking y squared common, we'll get y square minus 5 plus taking 4 common, we'll get y square minus 5 equals to 0. So we'll get y square plus 4 equals to 0 and y squared minus 5 equals to 0. Now, as x and y are real numbers, so y square equals to negative 4 will not be positive, as the square root of a negative number is not possible if it is real. And y squared is equals to 5, so y would be is equals to square root of 5. And when we square root, we can give both the positive and negative values. So, or we can even keep it as root 5, but we know that the complex square roots are conjugates of each other. So now we know that 2xy is equals to minus 4 root 5. So we can now write it as 2x into y. So y is root 5 is equals to minus 4 root 5. So now cancelling root 5, x value would be equals to minus 2. So one of the complex values would be minus 2 and the y value was taken as plus root 5 iota. So this will be minus 2 plus root 5 iota. And to find the other root, we'll substitute minus root 5 into the equation. So we will get 2x into minus root 5 is equals to minus 4 root 5. Root 5 cancels, negative cancels, the x value would be 2. But so the other square root would be 2 and the y value was minus, so that will be minus root 5 iota. So the two square roots would be minus 2 plus root 5 iota and 2 minus root 5 iota. Just one correction, what I said, I think I said they're complex conjugates. Well, not square roots. The root of a complex number, like if we find this, we solve it through quadratic formula, then in that case, they are complex conjugates when we are finding the roots, not the square roots. In question number 6a, by sketching a suitable pair of graphs, you have to show that the equation modulus x minus 2 is equals to 2 sine half x has only one root. So the way to do that would be, let's make the x and the y axis first. Now, if we have to sketch a graph of y equals to modulus of x minus 2, we can first simply sketch the graph of y equals to x minus 2. So assuming values of x and y, when x is 0, y is minus 2. When x is 2, y would be 0. So 0 and minus 2 is over here, let's say, and 2 and 0 would be over here. So the line would be like this. But as it's a modulus sign, so the final answer would be this part where we'll only consider the blue line as the graph. And this part below the x-axis will cancel out due to the modulus sign. And now sketching the graph of y is equals to 2 sine half x from 0 to half 0 to pi, basically 0 to 180 to understand it better. So now first taking the x value as 0. So when x is equals to 0, y would be equals to 0. Then we can take x equals to, let's say, pi by, so this is already 1 upon 2. Let's take it as pi over here. So if I take the value of x as pi, what I will get is y is equals to 2 sine of pi by 2. Sine 90 is 1, so y would be equals to 2. So so this point was, I think this point was 2, and pi means 3.142. So let's say if this is 2 over here, 3 is over here, and this value is 2 over here, and what we are getting is 2 over here as well. So the graph would be, the graph for 2 sine half x would be like this. As there would be this half x also we can understand like this. In 360, we'll have one revolution for sine x. So if it is half x, we'll have half a revolution in 360, or we can say even a quarter revolution in 180. So this is the only part that we will be making. And we can see that there's only one point of intersection from 0 to pi. And we cannot go beyond pi because, well, the domain is given from 0 and less than pi. So this point basically shows that there is only one solution. Now it says show by calculation the root lies between 1 and 1.5. Now we can write our equation as modulus of x minus 2 and then minus 2 sine half x equals to 0. We'll first substitute x is equals to 1 over here. So 1 minus 2 would be minus 1 with the modulus sign minus 2 sine of half. And then this will become positive 1 minus 2 sine of half. So this will be 1 minus 2 sine of, and the bracket will have 1 upon 2 in radian form, and this will be 0.04. So this answer is coming out as 0.04, and now substituting 0.5 over here, we'll get 1.5 minus 2 sine of, the x value is 1.5, so that will be 1.5 upon 2. So this will become minus 0.5, but with the modulus sign that will be a plus 0.5. So 0.5 minus 2 sine of 1.5 upon 2. And we are getting minus 0.86 in this case. So this change of sign basically means that the root lies in between 1 and 1.5. So we'll write change of sign from, it was initially positive to negative, when over here x was equals to 1 and negative 1 when x was equals to 1.5. Now in part C, it says use the iterative formula with an initial value of 0.1.03 to calculate the root correct to two decimal places. So this is the easiest step. All we have to do is substitute the first value. We know that is 1.03. So that will be 2 minus 2 sine of half into 1.03. Now substituting this in the calculator, we'll get 2 minus 2 sine of 1 upon 2 multiplied by 1.03, close the bracket, and the answer for the first answer is coming out as 1.0149. And now we'll substitute this back again into the equation, and we have to give all of our iterations to 4 decimal places. So substituting this back into the equation, we'll get 1.0149, and now the third value would be 1.02809, so that will become 1. And then substituting it back into the equation over here, we'll get 1.0281, and now we are getting 1.01658, so 0.0166. Again substituting it back at, so 0.166. So now we are getting 1.0266, and we have to make sure that we get our answer correct to 2 decimal place. So substituting this value back in, 0.0266, and we are getting 1.01789, so 0.179. And we have to show enough iterations to show that the answer is coming correct to the same correct 2 decimal place consecutively. So 1.0254, actually the difference between two consecutive values is decreasing in every step. 0.0255, substituting it back in over here, we will get 0.255 over here. Now this is 1.0188, 884, so 0.0188, and then substituting it back again, 0.0246, 1.02469, so 247. Now it's 0.1.0195, 0195. So basically, to 2 decimal place, the answer will always be 1.02. You can just do it one more time to confirm. So if I put 195 over here, it will again be 1.0240. So what we can see is from 241, this will become 241. So we can see each time the all of these values are decreasing, or this value is increasing towards 1.02, and this is decreasing towards 1.02. So the final answer for x would be x equals to 1.02. In question number 7, part A, we have to express 7 sine plus 24 cos in the form r cos of theta minus alpha, giving the value of alpha correct to 4 decimal place. Now, in the first step, we know that r is given as a squared plus b squared. So that would be equals to square root of 7 squared plus 24 squared. Substituting this in the calculator, that would be equals to 25. And alpha is equals to tan inverse of b upon a. So we'll get tan inverse of b is 24 upon 7. Substituting this in the calculator, and we have to make sure our calculator is in radian mode. So the value of alpha would be equals to, and we have to give our answer correct to 4 decimal place. So substituting this in the calculator, that would be equals to 0.2838. So that is the value of r and alpha. Once we have that, we can write our answer as 25 cos of theta minus 0.2838. In part B, it says, hence solve the equation 7 sine 1 upon 3x plus 24 cos 1 upon 3x equals to 24.5. Now, in the first step, we can write this as 25, and it was theta or x over here, and it was 1 theta. So if it is 1 upon 3, so this will also become x upon 3. So we can write this as 25 cos of, and we can write it as x upon 3 minus 0.2838 equals to 24.5. So 25 will divide on the left right hand side, and we'll get cos of x upon 3 minus 0.2838 equals to 24.5 upon 25, and then x upon 3 minus 0.2838 would be equals to, so this is not 28, this has to be 25. So that would be cos inverse of 24.5 divided by 25. Now substituting this into our calculator, we'll get, so shift cos inverse of 24.5 divided by 25. So that would be equals to 0.200. So x upon 3 minus 0.2838 would be equals to 0.200. So x upon 3 would be equals to 0.200 plus 0.2838. So zero point 0.2 plus 0.2838. And then we'll multiply this answer by 3. So plus 0.2838, and then multiplying by 3. One of the values would be x equals to 1.452. And to three significant figures, that would be 1.45. Now, what we also know is that cos is positive in the, so this is x upon 3. So cos is positive in the first and the fourth quadrant. So we make 0.2 over here and 0.2 over here. So the other angle would be 2 pi minus 0.2. So that would be written as 2 into pi minus 0.2 and plus 0.2838 multiplying by 3, but that is coming as a very large answer, so this answer will not be possible. So we'll have to check if there is any other solution in this range. One of the answers is x equals to 1.45. And can we take any other value? Let's check. Okay, so one more thing that we can always think about is, and I will draw a graph over here to explain it. So let's say a normal cos graph basically looks like this. So this is like a sine graph over here. Let me first sketch a rough cos graph. So this is what a cos graph looks like. And it is the same on the negative end as well. Now, this basically means a translation to the right. So in actually what that means is that when this is equals to 24.5 upon 25, that is around 0.9 something. So maybe one of the solutions has moved to the positive side. So what we can do is take the negative value as well and check if it lies in the range. So what we can do is check with zero point 0.2 as well, sorry, negative 0.200. And we'll get x upon 3 is equals to negative zero point 0.2 plus 0.2838, and then x would be equals to, so we'll put this in the calculator, minus 0.2 plus 0.2838, and then multiply by 3. So we are getting 0.2514 over here, and as it lies in our range, so x would be equals to x 0.25, and no other answer would be lying in this range. So it is important that we also check with the negative value as well, because if it lies within our range, as this negative sign adds up over here, and we have another value that lies in the range from 0 to pi. So the only two possible answers would be x equals to 1.45 and x equals to 0.25. In question number 8, the variables x and theta satisfy the differential equation, and that is sine 2 theta dx by d theta into 4x plus 3 cos 2 theta, and x is 0 when theta is 1 upon 12 pi. We have to solve the differential equation and obtain an expression for x in terms of theta. So in the first step, we'll bring the theta terms together. So cos 2 theta will divide on the left hand side. So we'll get sine 2 theta upon cos of 2 theta. Okay, so the d theta is in the denominator, so we had to do it the other way around. So we'll bring the 4x upon 3, 4x plus 3 in the denominator over here, and we'll write it as cos 2 theta upon sine 2 theta d theta. Now we can integrate both the sides. So integrating 1 upon 4x plus 3, that becomes ln of 4x plus 3, and the derivative of 4x plus 3 divides, so that will become 1 upon 4 and then 4x plus 3, and the derivative of sine 2 theta is 2 cos 2 theta, but we need a 2 over here, so we'll multiply by and divide by 2 at the same time. And now using this uh, integration property, that if we have the derivative in the numerator and the function in the denominator, this can be written as ln of f of x. So we have the function in the denominator and its derivative in the numerator. So this can be written as half ln of sine 2 theta, and then we add a constant plus c over here. Now, once we have done this, we use the initial values to find the value of c. X is 0 and theta is pi by 12. So we'll get half ln of 0 plus 3 will be 3, and equals to half ln of sine 2 times pi by 12 plus c. So sine, that will become pi by 6, and sine pi by 6 is half. So you'll get half ln of half plus c is equals to 1 upon 4 ln of 3. Now simplifying this, we can write it as 1 upon 4 ln of 3 minus 1 upon 2 ln of 1 upon 2 equals to positive c. Now, once we have this value, we can simplify it as well. We can bring this 2 in the numerator as well and write it as 2 to the power minus 1. Or we can take the LCM first maybe. So let's take the LCM. So if we take the LCM, uh, if I multiply this by 2, this multiply by 2, I will get 1 upon 4 ln of 3 minus 2 upon 4 ln of, and we can write it as 2 to the power of minus 1 equals to c. And now simplifying this, so we have a negative sign over here, or we can just write it as ln 3 to the power of 1 upon 4 minus ln 2 power minus 1, and this 1 upon 2 can become the power over here equals to c. So this will become ln of 3 power 1 upon 4 minus ln of 2 power minus half equals to c. And as they're dividing, I can write it as ln of 3 power 1 upon 4 divided by 2 power minus 1 upon 2. 2 power minus 1 upon 2 can come up in the numerator as well. And we can write it as, so well, it's getting quite lengthy, but we have space over here. Okay. So we can simplify the value of c and write it as c is equals to ln of 3 power 1 upon 4 into 2 power 1 upon 2 equals to c. Uh, and can we simplify this further? Well, we can write this. Well, let's leave this value as it is over here. Now, once we have this value of c, now we'll have to simplify the whole expression. So the expression was 1 upon 4 ln of 4x plus 3, and then is equals to half ln of sine 2 theta. So is equals to half ln of sine 2 theta. And in terms of, in place of c, we can write plus ln of 3 power 1 upon 4 into root 2. So that is easier to write. And we can also write 3 power 1 upon 4 in the root form. So let's say 3 upon 4, if I write 3 power 1 upon 2, and basically this is 2 square roots. So that is, we can write it as root 3 to the power of 1 upon 2. Okay, I can see a way we can simplify it further. So if I write it as ln of 3 root 3 into 2 to the power of half, it basically is the same thing, right? Because this half into half will become 1 upon 4, and 2 to the power half will be the same. And this half can come on the left hand side, and we can write it as 1 upon 2 ln of 2 root 3. So yes, this is a better simplified answer. We can write it as 1 upon 2 ln of 2 root 3. Now we have to give our answer as for x in terms of theta. So we have to make x our subject. Now in the first instance, what we can do is we have a common denominator over here. We can multiply by 4. So ln of 4x plus 3 would be equals to 4 upon 2, that is 2 ln of sine 2 theta. And then 4 multiplies by 1 upon 2 over here as well. So that will be 2 ln of 2 root 3. Now, before we simplify, we can write it as ln of sine square 2 theta, as this 2 becomes a power, and ln of, so 2 root 3 whole squared. And this remains as it is. So we'll get ln of 4x plus 3 equals to ln of, and that will be sine square 2 theta times by, so 2 root 3 whole square will be 2 square 4, 4 times 3 is 12. So finally we can write 4x plus 3 equals to 12 sine square 2 theta, and then 4x is equals to 12 sine square 2 theta minus 3. And finally x is the subject over here, and that will be x 12 sine square 2 theta minus 3 divided by 4. And that would be our final answer. In question number 9, in part A, we have to find the vector equation for the line through A and B. So the equation for a line is given in the form r equals to A plus lambda B, where B is the direction vector and A is the point on the line. So first, to find the direction vector, we'll find AB, and that is B minus A. So B minus A would be minus 2, 1, 3, minus 1, minus 4, and 2. So that would be equals to, the direction would be minus 2 minus 1 is minus 3, 1 plus 4 is 5, and 3 minus 2 is 1. So our equation would be r equals to, we'll use a point, any point we can use A or B. So let's use point A, that is 1, minus 4, and 2. plus lambda into the direction that is minus 3, 5, and 1. So that is the first part, the equation for the line through A and B. Now it says use a scalar product, find the exact value of cos BAC. Now to find the value of cos BAC, we can use this scalar product over here as this said. And the two direction vectors that will be used are, so this is A over here, this is B, and this would be C, and this would be cos of BAC. So the two vectors would be AB and AC. We already have the vector AB that is minus 3, 5, and 1. So this is minus 3, 5, 1 times by the second vector. So we'll find AC, that would be C minus A. So C is 2, 3, 5. So 2, 3, 5 minus A is 1 minus 4 and 2. 1 minus 4 and 2. So this will become 2 minus 1, 1. 3 minus 4, 7. And 5 minus 2 is 3. So we have the other direction vector, which is 1, 7, and 3, equals to the magnitude of the first vector, that is 3 square plus 5 square plus 1 square. We can ignore the negative sign, as when we square root, it will cancel out anyways. Into 1 square plus 7 square plus 3 square times by cos of BAC. So multiplying, we'll get minus 3 plus 35 plus 3 equals to root of the 25 plus 934 plus 135 multiplied by 49 plus 150 plus 959 cos of BAC. So BAC. So this will cancel out, and cos of BAC would be equals to 35 divided by root 35 into root of 59. We can simplify this, as this is power 1 and this is power half, they will subtract, and we'll get root 35 upon root 59 equals to cos of BAC. We can leave our answer in this form, or we can also write it completely as in the square root, as both are under square root. So that will be square root of 35 upon 59. Now in part C, it says find the exact area of the triangle ABC. Now to find the area of any triangle, we can use the formula half AB sine of C. Now the two lengths, and we can use this angle as well. So the two lengths are root 35 and root 59. So we'll get half into root 35 into root 59 into sine of C. Now this angle, we just left it as it is, but if you use our calculators, so if we do shift cos inverse, and we'll make sure our calculator in degree mode now. So this will be shift cos inverse of root 35 over 59. So that angle is 39.627. So we know that angle BAC, or the angle between the two lengths, is 39.627. So we can use sine of 39.627. So sine of this answer multiplied by root 59 multiplied by root of 35 and then dividing by 2, that is coming as 14.5. However, in the question it says find the exact area of the triangle ABC. So we will use a different method now. Now in place of this angle over here, we know the angle cos BAC is root 39 upon 35.59. So what we'll try and do is find a term for sine. So let's make it in the first quadrant. Cos is adjacent over hypotenuse. So adjacent would be root 35 and hypotenuse would be root 15. Oh, sorry. So this is not hypotenuse. This will be the hypotenuse. So this will be 59. So now applying Pythagoras theorem, c square root 59 whole squared would be equals to root 35 whole squared plus opposite. So let's call this x squared. So this will become 59 minus 35 equals to x squared. So x would be equals to 24 or root 24. Now once we have this value as root 24 over here, we can write sine of c would be root 24 upon 59. So yeah, so sine angle would be root 24 upon root 59. Root 59, 59 should cancel out, and 35 times 24. So we can write it as, uh, or can we can write it as 4 times 6 as well. So let's say we write half into 35 into root 4 into root 6. So root 4 will be 2, 2 upon 2 will cancel. 35 times 6 will be 210. So this will cancel out, and the final answer will be root of 210. And that's it. In question 10a, we have to find the quotient and remainder when x square is divided by 1 plus 4x square. So we'll write it as x square is divided by 4x square plus 1. So in the first step, we'll divide x square upon, we'll write it as 4 upon x square upon 4x square. This will cancel. So we'll get 1 upon 4 over here. 1 upon 4 will multiply by 4x square, and that would be equals to x square. 1 upon 4 into 1 would be plus 1 upon 4. We'll change the signs. So this will become plus, this will become minus, this will cancel. We'll get minus 1 upon 4, and we cannot divide it any further as there is no power of x, or that it is lower than the power of x over here. So the remainder would be equals to minus 1 upon 4, and the quotient would be equals to positive 1 upon 4. Now in part B, we have to find the exact value of x tan inverse of 2x dx. So we'll have to use integration by parts over here, and we know that the integration for, so let's say if we have the term, if we have it as 1 upon x square plus a square, when we integrate this, we get 1 upon a tan inverse of x upon a. So the integration of this term we know. So, and we cannot integrate tan inverse of 2x. So even though we use LATE, and algebraic function has to be taken as u, but as we know the derivative of this function, tan inverse function, so we'll take this as u. So u would be taken as tan inverse of 2x. So the derivative of tan inverse of 2x. So now if we just relate it over here, we'll know that, so if we have tan inverse of 2x, the expression over here, or the derivative of tan inverse of 2x would be, so du would be equals to, so the value of a is 1 upon 2, as if there is a 1 upon 2 over here, it will come up in the numerator, and there is no 2 over here. So what we can do is, in this instance, let's say a should a was 1 upon 2, so this we should have added 2 over here. So what we can do is we can uh, divide both sides by 2, maybe, yeah. So if I divide both sides by 2 over here like this, and this side by 2 as well, so this 2 and 2 will cancel. So the derivative of tan inverse of 2x would become 1 upon 2 into 1 upon x square plus the value of a would be 1 upon 2. So we'll get x square plus 1 upon 2 whole squared. Now simplifying this first, because otherwise it will get a bit tricky. So we'll get du is equals to 1 upon 2 into 1 upon x square plus 1 upon 4. Taking the LCM in the denominator, we'll get 1 upon 2 into 1 upon 4x square plus 1 upon 4. This 4 will come up in the numerator. We will write it as 1 upon 2 into 4 upon, so 4 upon 4x squared plus 1. This will cancel out, and we'll get 2 upon 4x squared plus 1. So this will be du. So du would be equals to 2 upon 4x squared plus 1. And v was x, so v will be d will be taken as x, so v would be x squared upon 2. Now applying integration by parts, what we'll get is the formula is vu minus v du. So v is x squared upon 2 into tan inverse of x, into u is tan inverse of 2x, minus v is x squared upon 2 into du is 2 upon 4x squared plus 1 dx. This 2 and 2 cancels out. So we'll get, we'll leave the left hand, this term as it is. And now we have to integrate. We have x squared upon 4x squared plus 1. Now we'll use part A in this case. We divided these two functions and we got the quotient and remainder as 1 upon 4 and minus 1 upon 4. So we can write this expression as 1 upon 4 plus, and just for revision, so let's say if I divide 7 by 3, so we get 2 wholes 1 upon 3, or we can write it as 2 plus 1 upon 3. So I can write it as 1 plus minus 1 upon 4 divided by 4x square plus 1. So simplifying this, I will get 1 upon 4 minus 1 upon 4 into 4x square plus 1. All right, so we'll get this in place of that expression. So we'll have, in place of this expression, we can write it as, okay, we can write this term later on. So this will become minus, and with the integration sign, we'll get 1 upon 4 minus 1 upon, so this will become 1 upon 4 into 4x square plus 1. So 1 upon 4 into 4x square plus 1 dx. So we can take the 1 upon 4 common outside to make things easier. We'll get 1 minus 1 upon 4x square plus 1. That is the term we have to integrate now. Now again, for this 1 upon 4x squared plus 1, we can use the tan inverse integration. But for that, we need the x squared term with a coefficient of 1. So we can write this as, 1 upon, taking 4 common, we'll get x squared plus 1 upon 4. And then the next step, we can write it as 1 upon 4 into x squared plus 1 upon 2 whole squared. Now we have it in the expression where the value of a is 2. Sorry, the value of a is 1 upon 2, like over here. And that will be 1 upon a into tan inverse of x upon a. So integrating this side now, we'll get, this is 1 upon 4 as it is. The integration of 1 is x minus, and this will be 1 divided by 1 upon 2. Not to forget, we still have the 1 upon 4 over here. Okay, it's getting a bit lengthy now, but anyways, so 1 upon 4 and the integration is 1 upon a. So a is 1 upon 2 into tan inverse of x upon a. So x upon 1 upon 2. We'll simplify it now. So this will cancel out with the 4. We'll get 1 upon 4 into x minus 1 upon 2 tan inverse of 2x. So this is the final integration, and this term before remains as it is, that is x square upon 2 tan inverse of 2x. And do we have to put the limits as well? Oh, wow. We have to put 0.5 and 0 as well. So we'll have to make some space over here. Now let's put in the limits. So the final expression, let's write down first. That is x square upon 2, and I hope I haven't forgotten this, 1 upon 4 over here. So that was 1 upon, yeah, no, I have taken that into consideration. So that is x square upon 2 tan inverse of 2x minus, that will become minus plus 1 upon 8 tan inverse of 2x and minus 1 upon 4x. So this There is no mistake so far, and now we can just simply plug in the limits. Obviously, we'll have to open the bracket first, so we can write it like this. Minus 1 upon 4x plus 1 upon 8 tan inverse of 2x. And now using our limits that are 0.5 and 0. So first substituting x equals to 0.5, we'll get 0.5 squared upon 2. Tan inverse of 2 into 1 is 1 minus 1 upon 4 into 0.5 is 1 upon 2 plus 1 upon 8. Tan inverse of 2 into half, that is again 1. And then subtracted from the lower limit, which is 0. So tan 0, 0, 0. So with the 0 limit, everything will cancel out and we'll have only this term remaining. Substituting this into our calculator. So zero point 0.5 squared is basically 1 upon 2 squared. That is equals to 1 upon so 1 upon 2 squared is 1 upon um 4 and 1 upon 4. This will become 1 upon 8 tan of 1 minus 1 upon 8 plus 1 upon 8 tan inverse. And I think there's an inverse over here as well. So yeah, that is tan inverse of 1. And this is also tan inverse of 1 over here as well. So simplifying this in the calculator, shift tan inverse, and we have to keep this in radian mode. So shift tan inverse of 1, that's pi upon 4. So that will become pi upon 32 minus 1 upon 8 plus pi upon 32. So 2 pi upon 32 will be written as pi upon 16. So the final answer will become pi upon 16 minus 1 upon 8. Now that was quite a lengthy one. And that can only be done in one attempt. If we have enough practice with these questions, at least you should have done 30 to 40 questions of similar type before the exam. In question number 11, the diagram shows the curve, the graph of y equals to 5 sine 2x cos square x and its maximum point M. We have to find the exact x coordinate of M. Now, as it's a maximum point, we know that dy by dx would be equals to 0. And as the terms are multiplying, we'll use the product rule. So u, we can take it as sine 2x and we can keep 5 common. So u dash, or the derivative of sine 2x, would be 2 cos of 2x. V will take as cos square of x. And when we differentiate v, so 2 will multiply. So we'll get 2 cos of x. And the derivative of cos x is minus sine x. We'll get minus sine x, or we can write it as minus 2 cos x sine x. Now applying the product rule, you'll get vu dash plus uv dash. So this is u dash and this is v dash. So vu dash would be cos square x into 2 cos 2x. So cos square x into 2 cos of 2x plus uv dash. So that will be sine of 2x multiplied by minus 2 sine cos, and then the whole expression is multiplying by 5 over here. So we'll get 10 cos square of x cos of 2x minus sine 2 of x into 2 sine cos. Now to make this positive, we can, and we'll put it equals to 0 as it's a maximum point. We'll take it on the left hand side, we'll get sine 2x into 2 sine cos is equals to 10 cos square into cos of 2x. Now to solve this equation, well, I think we can cancel this cos and cos over here, and cos sine 2x upon cos 2x, we can write it as sine 2x upon cos of 2x, and 10 upon 2 will become 5, and this is cos upon sine. So this will be tan of 2x is equals to 5 upon tan of x. Now to solve this, what we'll do is we can use the identity over here for tan of 2x. That is basically 2 tan of x upon 1 minus tan squared of x, and that is equals to 5 upon tan. Now cross multiplying, we will get 2 tan square is equals to 5 minus 5 tan squared. So 2 tan squared plus 5 tan squared, that will make it 7 tan squared equals to 5, and tan squared would be equals to 5 upon 7. And just one correction, we did not multiply the 5 over here. So we had to multiply by 5 over here as well. This would have been a 5 over here. This would have been a 5 over here as well. So this would become 5 times 2. So this would have been 5 into 2 tan upon 1 minus tan square equals to 5 upon tan. So now if I cross multiply, that would become, so 5 times 2 is 10. So 10 tan square is equals to 5 minus 5 tan square. So that will be equals to 15 tan squared equals to 5. And finally, I can write tan squared of x equals to 5 upon 15, which is equals to 1 upon 3. And now finding the value of x, so we'll do shift tan inverse of root 1 upon 3. So x would be equals to tan inverse of root 1 upon 3. So shift tan inverse of root 1 upon 3, and that is equals to pi upon 6. So the x coordinate would be pi upon 6. Now in part B, by using substitution u equals to cos x, we have to find the area of the region bounded by the curve, the x-axis, between these 2 points and the line x equals to 1 upon 4 pi. So the equation is 5 sine 2x cos square x. So we have to integrate with the limits 1 upon 4 pi and 0. And our equation is, again, what is it? 5 sine 2x. So that is 5 sine 2x into cos square of x dx. Now whenever we are using substitution, the first thing we do is we find du by dx. That would be equals to minus sine of x. So dx would be equals to minus du upon sine of x. So in place of dx, we will write, and in place of sine of 2x, we can write 2 sine cos as the identity. In place of cos square, we can write, well, we can write already. And in place of dx, we'll write minus du upon sine of x. So this will cancel out. And in place of cos, we will have u. So this will become 10 into u cube. And there's a minus sign over here, du. And now we'll change the limits as well. So u is equals to cos of x. So we'll write cos of 1 upon 4 pi. So u would be equals to, now cos of 1 upon 4 pi, if we substitute this in the calculator, that is equals to root 2 upon 2. That is basically 0.707. And when we substitute cos of 0, that is equals to 1. So we are getting the upper limit with the lower value, which basically changes the sign over here. So we can remove the sign and write it as 1 and root 2 upon 2 as our limits. Now integrating 10u cube, we'll get 10u power 4 upon 4. 10 upon 4 is 5 upon 2. We'll get 5 upon 2 u to the power of 4. And we have integrated this. Now we'll plug in the limits. So the first limit is 1. Yes, the first limit is 1. So we'll get 5 upon 2 into 1 minus 5 upon 2 into root 2 upon 2 to the power of 4. So root 2 to the power of 4 basically means power half into 4. So that will become 2 squared. So we'll get minus 5 upon 2 into 2 squared upon 2 to the power 4, which is 16. And this 5 upon 2 remains as it is. And then finally, simplifying this, we'll get 5 upon 2 into 4 upon 16. This will cancel out. We'll get 5 upon 8. So 5 upon 2 minus 5 upon 8, multiplying this by 4, this by 4, we'll get 20 minus 5, which is 15 upon 8 as the area under the graph for the limits pi upon 4 and 0. So the final answer will be 15 upon 8.